Hello, my rubber hearts. Today we have a very special episode. I'm at Gradient Compounds in the Netherlands, sitting down with their CEO and co-founder, David Brown. After qualifying as a mechanical engineer, David began in electronics research before embarking on an international career, implementing new technologies around the world. In the 1990s, he founded a company together with his two brothers, both engineers, to commercialize new technologies. In 1997, they were approached by Dr. William Bill Watson, who introduced him to the world of rubber and mechanochemistry. Nearly 28 years later, he is still playing with rubber. Gradient Compounds is working on something that could shift how we think about rubber waste. They've developed a technology that can decrosslink cured rubber without using heat or aggressive chemicals. That means compounds that were once considered final and unchangeable can be broken down and reused. This matters because the rubber industry generates a huge volume of production scrap and post-industrial waste. Most of it ends up in landfills or incinerators. But here, the team at Gradient is proving that it doesn't have to. Their technology supports a more circular approach, bringing old rubber back into the loop and cutting down on raw material demand. In this interview, we'll talk about the origin of the company, how the technology works, and where it fits into the future of sustainable rubber manufacturing. Let's get into it. David, first of all, thank you for having us here.
Oh, it's a pleasure and welcome to Gradient Compounds.
Thank you. Before we dive into the technology, I want to start with the story of Gradient Compounds, because when we spoke before, your excitement about how Gradient Compounds came to be really stuck with me. It's not just a company with a clever process, it feels like a mission. So I want to give you the space to tell the story. Can you tell us how Gradient Compounds got started?
Yes, it's a new technology, but with a very long history. As you mentioned in your introduction, we were first approached by Bill Watson, in the 1990s. And he'd been doing work on mechanochemistry in the 1940s and 1950s. He retired in the 1980s and went back to university and started to look at how to destructure or pull apart a crosslink system purely mechanically. And he came to us, and that really kicked us off looking at how to solve this problem.
What was that first spark that made you think we can actually decrosslink rubber? That brave moment where you thought, let's build a company around it?
Well, as you said, my brothers and I were looking at taking new technologies and building companies. When Bill came to us with his first proof that he could actually do this mechanochemically, we saw a huge opportunity. Mm-hmm. He had a batch technology, and we took that as far as we could, and then developed a continuous, and that is the start of Gradient.
What problem were you seeing in the rubber world that made you want to take this on?
Well, there's more and more pressure on using resources efficiently. Mm-hmm. And if you look at the plastics world, you can take a plastic, reheat it, and reuse it. Unfortunately, you can't do that with rubber because of the crosslinks.
Yes.
And the challenge was to actually break those crosslinks and leave the rest of the material as whole as possible, so you could actually retain that value of the material. And that was the challenge.
15 years ago, when I first walked into the rubber lab, that is the first thing that I was taught, that rubber, once it's cross-linked, it's forever.
Absolutely. and in fact, part of what we're doing is actually explaining that although everyone considers it to be an irreversible process, under certain conditions, you can actually break those crosslinks.
What was missing in the industry at that time?
I think that a lot of people have been looking at recycling rubber, mm-hmm. but using standard equipment in the industry. And that equipment hasn't been designed for this purpose. So for us, what was missing was actually dedicated equipment, starting off from fundamental physics, that actually will rupture the crosslinks, but keep the material cool, mm-hmm. so you're not damaging the material thermally.
You're not just solving a technical challenge. You are also tapping into the sustainability conversation in a real practical way. How did that become part of your company's DNA from the beginning?
Well, I think that what we were looking at was a good engineering solution to a technical and commercial problem in the industry, or mm-hmm. an economic problem. using resources efficiently is absolutely important in all areas. And this technology gave us an ability to address that. And that's why it became special to us. I've given you a little bit of a background of Gradient, but perhaps it would be useful to go and see and discuss the technology in more detail. So if we can move over to the production process, we can carry on.
Sure. All right, David. Now that we came to the place where the magic happens, let's get into the heart of the technology.
Sure.
So, David, can you tell us a bit more about the steps that the material goes through in your technology?
Yes, certainly. Unfortunately, we haven't got the system running today because we're doing this interview. But what happens is material comes in into this area here where it's inspected and sorted to make sure that it is what we expect and it's clean material. It then goes through a granulation process where we reduce it because at the moment we're processing materials that come in lots of different sizes and forms and shapes. And what we need is a consistent shape that we can feed into our machines in a controlled way. So we reduce the material down to a 3 to 5 millimeter particle size. We then feed that, we store that, that's what the boxes are on the far side there. We then take that material and feed it in a controlled way into the start of our process, our first machine. And there we're controlling the speed, the feed, the temperatures, and the machines themselves each have 6 mixing heads in there. So the material will go through 6 stages of mixing. And we can control each mixing stage, both in terms of the amount of stress we put into the material and also the temperature that it sees. So we manipulate the material 6 times. It then comes out of that machine, goes into a second machine where it's manipulated a further 6 times.
Okay.
So the poor material at the end of the process has been through quite a bashing. But the idea is to do that in such a controlled way that we're not damaging the polymer. We're only looking at the crosslinks. The material comes out at 60 to 80 degrees C. It then runs through a cooling system where it's brought down to about 35 degrees C, and then goes through a packaging system where what we've found is that our customers are putting these materials back into an internal mixer, and we can give them a bag of material at the correct weight
Yes.
for their recipe in their mixer.
This gives a great flexibility for clients who want to load the material directly into the knitter.
Yes,
Absolutely.
absolutely. And in some cases, we'll also do it in low melt plastic form. So they can just throw the whole bag into the mixer.
This process developed by Gradient Compounds is not just a variation of existing methods. It's something quite different. Can you walk us through how the technology actually works, especially the inline process? How are you able to break crosslinks without using heat or harsh chemicals?
Okay, the basic hypothesis is that if you have a cross-linked material and you stretch it, you put it under stress to a point where you start to break chains, then the chains that will break are the weakest. So what you have to do is create a condition where you're constantly doing that in a 3-dimensional matrix to break the crosslinks. What we have is a special mixer which moves the material in a particular way, and we can change the amount of energy or the amount of stress we put into the material as it goes through the machine.
So, in a polymer matrix, your technology works on the basis that the crosslink is the weakest link.
Yes, that's what we're looking to do. We're looking to create the right condition to do that. And what we have also found is that doing it cool allows us to put the mechanical energy in a far more controlled way. So we're typically operating at 60 to 80 degrees C. So a lot of what we do is about extracting the heat at the same time as we're mixing.
So, you are also avoiding degrading the polymer because of the heat.
Well, that's a very useful side effect, absolutely. The problem with using standard rubber equipment is that very often you have to put very high temperatures into the material to get it to move. We're doing the opposite. We're actually putting cool material in and manipulating the cool material.
Everything under 60 degrees.
Well, 60 to 80 degrees is typically when you do the optimum. Again, it depends on the TG, it depends on the material that we're processing. But what is particularly attractive about this is that it is a principle which applies to most polymers and most cross-linking systems.
I'm happy you said that because my next question was specifically about this. What kind of polymers can you process?
Well, we've done most polymers now, from natural rubber, SBRs, through to AEMs and butyls. We also do FKMs and FFKMs.
Oh.
We even do cross-linked polyethylenes.
Oh, wow.
So if there is a cross-link there, we look to break it.
Do you find that some are easier than others?
Yes, typically the higher the cross-link density and the more fillers you have in a material, the more difficult it is to work. So
Understood.
low cross-link density materials with low fillers, think of something like an elastic band, are very easy to process.
Okay.
And what comes out is almost a gum. A very highly cross-linked material with lots of fillers will tend to come out slightly more powdery. But if you put that powder, that fragmented material onto the mill, it will sheet up.
So your technology works on all curing packages that are normally being used in the rubber industry?
Yes, I mean, that's another question I often get asked. What
I
about
imagine.
peroxides? You know, we started off looking at sulfurs because the bond energy of a sulfur is lower. But we then moved on to peroxides, where it's more of a stiffness and rotation angle argument. But we've also done bisphenols and metallic cure systems.
What is the difference in between a cure system like sulfur and a system like a peroxide?
Well, from a mechanical point of view, in what we're trying to do, and that's where I don't have to be a chemist. I'm a simple mechanical engineer.
Yeah.
But what we're looking to do is we're looking to break the bonds, and we're looking to seek out the weakest bonds. And really, the chemical structure of that bond is less important. There is a secondary issue, and that is obviously when you break a bond, you have a free radical. And how you do that free radical manipulation and capture, that's a secondary part of what we do.
Can you tell us more about that?
It's about how you encapsulate the free radical. And basically what you want to do is you want to make sure that that free radical is no longer available. You want to actually make sure you have complete rupture. And the way that you manipulate and move the material influences that. The other thing that we do see is that because we're processing cool, if there is any additional cure left in the system, then we actually detect that even after we've processed it.
I was actually going to ask now, if you still have free radicals,
Yeah.
do they contribute to the cross-linking when you recross-link the rubber?
Normally, the lifetime of a free radical is fairly short. So it's more about manipulating the material in our process. But any residual cure left in the system will obviously affect the next stage.
From a processing perspective, how does the decross-link material compare to virgin material?
It really depends on what the starting point was of the material. As I said, if you have a material with lots of crosslinks to break, then normally we can recover the tensile strength. In most cases, also the elongation of break. But what we do see is that the viscosity is sometimes higher, and very often that is the result of what happens during the original cure, because we're comparing it to a virgin material which has viscosity modifiers as well as process aids and everything else in there. And that's material that's been taken through a heat transformation. We're focusing on the crosslinks, but there are lots of other chemical reactions that take place and outgassing during that heating process. And that can sometimes have a bigger effect than just breaking the crosslinks. And it's one of the things that we've been looking at now in far more detail, because adding some of those ingredients back allows us to recover the viscosity and the processability of the material, as well as the mechanical performance.
So besides adding the cure package after your process, anyone can add volatile and is lost during the vulcanization process?
Absolutely. We call this a master batch. It's basically a non-reactive, unless there is additional cure still in that, a non-reactive material, which needs to be formulated by reincorporating materials that have been lost during the curing process. Another thing to remember is that this is a material that's gone through a secondary mixing process.
Yes.
So in some cases, you will also have better dispersion of some of your ingredients.
So David, what happens if I want to decross-link a rubber part that is made up of 2 or more rubber formulations?
It's a good question, and we get asked it often. Obviously, the extreme extent of that is something like a car tire,
Yes.
where you'll have 4, 5, 6 different polymers and recipes in a product. What you typically get is a mixture of those, because effectively we've got a mixing process.
Yes.
So we will mix the material,
Mhm.
and what you will get out at the end is the best performance of the weakest material that's in that mixture.
So, David, how do you introduce your technology into the industry?
That's a very good question. One I've been working on for 28 years. Um, the industry is very skeptical.
Yes.
And so everything we do has to be trialed, it has to be proven for each individual material. And when we looked at it, we decided that the best thing to do was to take a clean material
Mhm.
with a known history and to start there, because then we were actually ruling out a number of other variables from the process. And so we are looking at scrap material, material that's generated during a normal production process, taking that material through our process and returning it in a form
Mhm.
that the customer can put it back in as a replacement of their virgin materials. That's obviously a very high bar to get over,
Mhm.
but that's where we're starting.
So, how far can you go with the addition of the reclaimed material into the virgin material?
Again, a lot depends on the scrap rate in the factory.
Mhm.
Clearly, some of these materials we can actually get good properties at 100%,
Mhm.
but nobody wants 100% scrap rate in a factory.
Yeah.
So normally what we're looking at is 30%.
Mhm.
As a maximum. And the reason for that is if you go above 30%, you get an accumulation of recycled material as you go in time. It's
Yeah.
something that was found in the aluminium, glass, and steel industries. 30% gives you a sustainable material flow.
So that would have been naturally my next question. How many times can you reclaim this material? Did you notice any issues?
Again, it depends on how completely we decrosslink it and how much damage we do to the polymer backbone.
Mhm.
In most cases, you can recycle it a number of times. Ideally, if you're below the 30%, the number of times you recycle drops away very quickly. To give you an example, if you were to recycle 90%,
Mhm.
then the second time, 90% will be recycled, but 81% will have gone through the process twice.
Yes.
If you're only recycling 10%, the next time 1%, and the next time 0.1%.
Mhm.
So it drops away very quickly. With 30%, it drops away after about 4 times.
What are the strategies that your clients are usually using when using reclaimed material?
A lot of people are looking at this as a totally new venture,
Mhm.
and what they have to do is manage risk. So we look for products or areas where the technical risk is low and the downstream liability
Mhm.
is low. For instance, if you are making a component which goes into a car, and
Yes.
something goes wrong and the manufacturer needs to recall the car, the costs are exorbitant and
Yeah.
nobody will start with a project like that. But if you have a lower risk project, that's where people start. It's all about managing risk.
Can you share with us some success stories?
One of the problems that I have is that all the work that we do is under NDAs.
Mm.
So I cannot say anything unless my customers tell me.
Okay.
Having said that, I'm currently working on a project in the UK where a major automotive manufacturer has said that they will go back and look at their specifications to allow a higher recycled content. And so I'm working with a tier one manufacturer of components for them and their compounder.
Mhm.
And that's actually quite a successful project. But there are lots like that. There are a number of products that are actually out there in the market with our materials in them, but we're not allowed to talk about them.
Now, let's talk about the elephant in the room. The product that everyone wants to know when will be recovered, reused, or recycled tires.
Ah,
Yeah.
yes. Well, it's more than 50% of the application of rubber, so it is an important area to look at.
Yeah.
A tire is a very highly specified material or component, which actually consists of a number of different materials. So recycling it is not trivial. Particularly end-of-life tires, because they will have gone through a number of heat cycles, the material will have been degenerated as well. We can take tires in different forms. We can take a whole granulated tire
Mhm.
with all the different components in it. We can process it, and we can provide a material which has useful function. It's not as good as some of the initial components in the tire, but it's still of useful function, and it can be used for a wide number of different applications. That's one area that we are looking at. The second is we can take specific parts of the tire, like the tread. We can recycle that at a much higher level and put it back into tread. And that's, again, an area that we're looking at, and we're working with tire manufacturers on that. In general, though, we as Gradient tend to focus on the factory scrap, which, because it still belongs to the customer, never enters the waste stream.
Yes.
As if you look at tires, they're typically at the end of their life.
Yes.
And so they've entered the waste stream. And there is a load of legislation around the management of waste.
And handling, and yes.
All the handling, the storage and transport. And also there's a question of, when does a material that's been put into the waste stream no longer act as a waste? When can it be considered as a raw material again? And again, there's a lot of legal red tape around that. So what we have done is we've set up a joint venture with a company that granulates tires, Styrene-Butadiene here in the Netherlands. And we've set up a company which we call Rerun Rubber Products. And that looks at taking end-of-life materials with our technology and putting the materials back into the market for applications.
In your experience, David, what is the shelf life of a reclaimed material that's been through your process?
If we've got a material where we've broken the crosslinks and it's inert, there's no residual cure package in it, then it's like a master batch. It can sit on the shelf for a long period of time and you can just recover it. If there's any residual cure in there, then you have to watch out for that, and that will limit the cure time. But that differentiates what we're doing from a lot of the high temperature materials, which actually go off very, very quickly.
Do you feel there is still a need and a desire to go sustainable nowadays?
I think the topic of sustainability is always high on anybody's agenda. And in fact, I've noticed over the last 5-6 years that more and more companies are focusing on sustainability and making it one of their primary goals. The problem within the rubber industry is, how do you do that? It's not immediately easy because of the technical challenge of cross-link systems.
And finally, I want to zoom out a bit, because this isn't just a technical solution. It has wider implication for how we handle rubber waste. How does this process contribute to a circular approach in the rubber industry?
Well, any circular approach requires the material that's going to be reused to have a value. And what we aim to do is to maximize the value of that material to a point where scrap that's produced during the production process can be put back in to replace virgin materials and not drop the performance of the product.
So instead of losing money with handling with the waste, you are giving it a new life and a new value.
Absolutely. You're conserving the value. If you think of what you do in industry, particularly in the rubber industry, you're taking materials, you're mixing them, you're manipulating them, and you're making a product. The scrap in a factory is at that very highest value. It's a pity to just throw that away, or in fact to pay to throw it away. We can take that material and put it back in and reuse it.
Have you done any life cycle assessment or quantified the CO2 savings that a rubber manufacturer can obtain while using your process?
Yes. We know very well what we require in our process. Because we're processing such a wide range of materials, each one has its own LCA attached. What we do is we look at what it takes to take that material back into a form it can be reused, and typically it's about 0.25 if you're looking at CO2 kilograms per kilogram of rubber. But there are other issues that we look at as well. For instance, if you look at our process, if we're running only natural rubber, then in a year we would basically conserve 3 square kilometers of plantation or equatorial rainforest.
True.
Per plant like this.
The implications are wider.
If you look at oil for SBR, then it's about 1,200 tons of oil.
Oh, wow.
For running this process for a year. So there are huge impacts which go beyond just the simple economics and the CO2 footprint, if you like. The amount of energy that we use is less than 1/10 of the energy that you would need to make a new product. So again, these are things that need to be taken in as a part of the LCA.
It goes far beyond saving raw materials. It trickles into what it takes, the effort it takes to obtain those raw materials.
Absolutely.
Yes.
And I think that as a society, we need to focus on that.
Absolutely. David, thank you for sharing all that. It was a really insightful look into what gradient compounds is doing and why it matters. Now that we've covered the theory and the technology, it's time to put it to the test. In the next episode, I will take one step further and head into the lab to work directly with decrosslink rubber produced using gradient compounds process. I will show how the material handles on the roll mill, how it mixes with the standard curing package, and whether it behaves like a conventional compound during reprocessing. We will also run an MDR and other key tests to evaluate whether the rubber can successfully be revulcanized, demonstrating its potential for real reuse in production.